So for the second half of chapter 27 audio lecture here, what I want to do first is review some things we talked about in the first lecture video for this chapter, and then talk about a couple of remaining topics in 27, and then I'll upload a new video for chapter 28. So you may recall in the previous lecture that we kind of looked at some qualitative observations of how magnets behave, right? We saw that opposites attract, like repel. We saw that each magnetic object has two poles, a north and a south, and the north pole acts kind of like a positive charge, if you will, right? Where electric field lines come out of positive charges, well, magnetic field lines exit the North Pole and enter the South Pole. So the South Pole is kind of analogous to a negative charge, okay? And the cool thing about magnetic materials is that you have both poles on one object always. So there's no single pole, there's no single North Pole, and there's no single South Pole in existence on anything that we know. So everything that's magnetic is composed of a north and a south pole. And similarly to charges and electric field and electric forces, objects that are magnetic can attract non-magnetic objects in the same way that charged objects can attract uncharged objects. And then finally, what we're going to be talking about a lot coming up in the next chapter is how currents create magnetic fields, right? Because moving charges create magnetic fields. Therefore, current, which is composed of millions and millions of moving charges, are going to create magnetic fields as well. And if you were to put a compass on top of a current-carrying wire, you would see that compass needle move in response to the magnetic field being created by the current flow. So the first thing we kind of talked about is a right-hand rule. And that right-hand rule helps us determine the magnetic force direction of the force on a particle that is moving in a magnetic field. So let's say that we have a positively charged particle, positive Q, and it's moving with velocity v in a magnetic field pointing to the right. And the velocity direction is perpendicular to B, okay? Well, in order to figure out the direction of the force that the particle feels in that field is you would sweep your fingers in from V into B, and then of your right hand, and then your thumb would point up, right? So a picture of this is if you take your right hand and you point your fingers in the V direction, and then in order to do that, your thumb is pointing up like that. And then you start curling your fingers into B, right? Curl those fingers, and your thumb would be pointing up in order to do that. And so mathematically, what's going on, what this hand gesture is telling you mathematically, is that this force vector is perpendicular to the plane created by V and B. Okay, so vector V and vector B, those are two vectors. We can use two vectors to define a plane, okay? And this force vector will be perpendicular to that plane, okay? Just like this, perpendicular. So I just drew it there so that you could see that it's just sticking out the face of that plane, okay? So this is how we determine the magnetic force on a moving charged particle. And we did this example. This explains the right-hand rule. Here you can visually see the right-hand rule in action if you click on this video. Okay, here it is in a kind of a sketch. And then the next thing we talked about was that, okay, well, let's generalize this a little bit, right? We know that current carrying wire, right, or a conductor with current flowing through it, well, that's made of a bunch of particles moving with velocity v, right? So therefore, it should also create a magnetic field. And this magnetic field direction, so we're kind of switching gears here, right? We were talking about the force that a charge feels. Now we're talking about the magnetic field created by the moving charges in the current. And we're going to use another right-hand rule to determine that. And this right-hand rule is you put your thumb in the direction of the current, and then your fingers will curl around, okay, in the direction of the magnetic field. So magnetic fields are basically found as circles around a current carrying wire. And the perspective at which you are looking at the wire is going to play a huge role in figuring out what direction the B field is, because it depends on where you are in relation to the wire. For example, if we're looking at the wire long ways like this, okay, those circles are going to be coming out at you on the top of the wire and going into the page below the wire. Okay, let's look at another perspective. What if we're looking straight down the wire? Okay, so the current direction is coming out directly at you. So if you stick your thumb pointing out of the screen, okay, your fingers of your right hand would be curling in the counterclockwise direction. Okay, and let's look at some important directions here, or some important positions around this wire. So above the wire, okay, directly above the wire, the magnetic field is pointing in what direction? It's going to be pointing to the left, okay, right? You take the tangent of that circle there, B is going to be pointing to the left above the wire. What about below the wire? B is going to be pointing to the right at any point below the wire. Right? If you take the tangent to that circle, it's going to be pointing to the right. Pretend there's a circle there to take the tangent. Right? B is pointing to the right. What if you're to the right of the wire? If you're directly to the right of the wire, the B field will be pointing up. And if you're to the left of the wire, the B field will be pointing down. Oops, purple. Whatever. You get the idea, right? And so the opposite will be true if that current is flowing away from you, right? Your thumb would point into the board, and then your fingers would curl in the clockwise direction of your right hand, that is. And then everything would be opposite to this case on the right. Okay? So perspective is important when you're determining what direction the magnetic field is in relation to a wire, a current carrying wire. And so this is going to be really important to understand when we get to chapter 29, I believe, or chapter 30. So let me go ahead and make sure I don't get any weird notifications. And so I kind of breezed over magnetic flux because we spent a lot of time working on electric flux, and it's literally you're doing the same mathematical operation, right? The only difference is we're using a B field instead of an E field. So the math is exactly the same. The way that we define the magnetic flux, the most generally, is the exact same way we defined electric flux, except we replaced E with B, okay? The other difference is that when we apply the Gauss's law to a magnetic field, the right-hand side is always 0, And that's because of that north and south pole. Right? If we have a magnetic object and magnetic field lines flow into the South Pole and out of the North Pole, and we enclose that object in an arbitrary surface, so let's just, or an arbitrary, Gaussian surface, let's say a cube or a square or whatever, right? It's inside something. You're going to have just as many field lines pointing out as you would do pointing into the surface. They will always cancel out. All right, look at those field lines, right? They come out of the north into the south. Compare those to that of electric field lines of a particle, right? The electric field lines of charged particles, they basically point in one direction, either directly toward or directly away from that charged particle. But when we look at magnetic field lines, you have the toward and the away in one object, okay? So those field lines, I think there, right? Away from north into south, away from north into south, okay? So you have that field line basically canceling itself out. And so you will have no net flux through any closed surface. So that's just some interesting math there. Okay, units of magnetic field, Tesla. Units of magnetic flux, Weber, which is a Tesla times area, right? B times area. So let's do this example real quick just to kind of like get warmed up. I skipped it over in the last lecture, but let's do it real quick here. So here we go. So we have a B field, okay? We don't know its value. We just know that it's uniform, which means it has a constant value everywhere in space. We have an area, and we're given the dimensions of the area. And we're told that the flux is 0.9 milliwebers. We want to find what is the magnitude and direction of the magnetic field. What is the magnitude of the magnetic field and the direction of the area vector A? So this is kind of the cheat sheet here, right? It's the answer, but let's kind of work through it together. So what are the givens in the problem? Well, we're told that the flux, the magnetic flux, is 0.90 milliwebers, which is 0.90 times 10 to the minus 3 Webers, which is a Tesla times a meter squared. Okay. And, well, we know that that's equal to B vector dot A vector. And I'm using this expression of the flux because we're told that B is uniform. If B was not uniform, I would need to use the integral version, okay? But we don't need to do that because B is uniform. So that number, 0.9 times 10 to the minus 3, that is equal to B dot A. What do we know about A? We're actually told that the magnitude of A, right, the area, is 3 centimeters squared. Okay. That gives us 3 times 10 to the minus 4 meters squared. And the direction of A. So we are told that the angle between this sheet, this area, okay, and the field is 30 degrees. So not the normal vector of the area, but the sheet of the area itself. Okay, that's what this 30 is telling us. So we can draw that as if we make the B vector to the right and leave that, you know, in a direction that we fully understand, then the area sheet, the sheet itself, not the area vector, but the sheet itself is at an angle 30 degrees to the B field. Okay? So if this is the sheet, and this is us looking directly down the side of the sheet. So if this was a sheet of paper and we're looking at it from its edge, we wouldn't really see the paper. You would just barely see it, right? You would see mostly the edge. And so that being said, the normal vector of the sheet, right, which is the vector that we use to describe the area vector, that's going to be 90 degrees to the sheet. Okay, so here's our area vector. And so if we do a little bit of geometry, right, because what do we need? What we need is we need the angle between B and A in order to do this dot product, right? We need the angle between B and A because we know that B dot A is simply BA cosine theta, or theta is defined as the angle between B and A. So that's what we're here to figure out. We're told that the angle between B and the sheet is 30 degrees. So that means the angle between A and B is going to be this value here, right? Which would be 180 minus 90 minus 30, right? Because this whole thing is 180. We know this is 90, and we know this is 30. And so what that gives us is 60. That's our theta. So we got almost all the pieces of the puzzle. What are we asked to find? We are asked to find what is the magnitude of B, right? Well, we know that 0.90 times 10 to the minus 3 Webers equals B A cosine theta. We don't know B, but we know A is 3 times 10 to the minus 4 meters squared. And we know that theta is 60 degrees. So now we can solve for B. Put that in the calculator. Six. All that for the number 6. Okay. We get 6 what? 6 Tesla. All right, 6 Tesla. That's the magnitude of B. And the second thing it wants to know is what's the direction of the area vector A? So the direction of the area vector A, well, I mean, in reference to what? I guess in our picture, right, we can say that A, so let's just do this. So what is the direction? So in reference to B, so we would say is that A is 60 degrees from B. We also know that A is 90 degrees from the plane of the paper, right? That's just basically the definition of the area vector. And you could also say that I mean, that's pretty much all we need to describe the direction of A, right? Because we don't have an XY coordinate system on here. So there's really no way to define the direction of A in terms of a coordinate system. So we're just defining it in reference to some other vectors in the problem. Okay, so that's basically the magnetic flux example. We're basically doing the same procedural steps as we did for electric flux. So we're kind of, this chapter skips around a little bit. Let's look at this. I know why it skips around, because we're talking about magnetic field lines, right? So this is in the context of magnetic field lines. You have to understand how magnetic field lines work in order to do flux, right? Because flux is an operation of dotting or multiplying the B field vector and the area vector. So in this conceptual question here, your knowledge and understanding of magnetic field lines is what's being tested. So let's take a look at it. So it says, imagine moving along the axis of a current carrying loop in this figure right here. Okay, so this is the axis, okay, of a loop. Goes straight through the middle of the loop. Starting at a point to the left of the loop, so starting somewhere over here and moving along that axis to over here to the right, how would the strength of the magnetic field change as you move along this path? So how would the strength of this field change? Well, recall that current carrying wire produces magnetic fields. And think about when you're far away from the source of a field. So let's use our knowledge of electric fields as an analogy, right? Let's say that here's a positive charged particle. Here's the electric field lines, right? And they get a little bit smaller as you go farther away. So the farther away you are from the source, right, the weaker the field. The closer you are, the stronger the field. The same is true for magnetic objects, okay? That current carrying wire, that is the source of the field. So if you are close to it, that field is going to be strong. If you're far away, that field is going to be weak. So if we are all the way here to the left, that field is going to be weak. And as you approach that wire and get closer and closer to the center of it, it's going to get strong, right? So the strength will increase. And then as you get far away again, it will decrease. So for part A, okay. For part A, would it be 1, 2, or 3? So 1 would be same along all points along the path? No. Would it increase and then decrease? That sounds about right. Would it decrease and then increase? No, right? It would increase as you approach. And then as you leave, it will decrease, right? So number 2. How would the direction, so part B, how would the direction of the magnetic field vary as you move along the path? Let's erase these lines. How would the direction of the magnetic field vary? Well, that is basically, you can look at the arrows on the magnetic field line and you will see that the direction of the magnetic field is the same, right? The direction of the magnetic field as you move along this line right here is always going to be to the right. Okay, so it wouldn't change, no change. Be constant, okay? So this is just basically understanding magnetic field lines and understanding how the spacing relates to strength, understanding how the distance you are from the source of the field relates to strength, and understanding these arrows and how they give you the direction of the field. okay? So if we were on one of these curved lines and we were asked what's the direction of the field right here, you would take the tangent to that curve, okay? So the direction of the field at that particular point would be like that. The direction over here would be like this. So you're always taking the tangent to the curve. The tangent of a straight line is, is the line itself. So that's why we're always pointing to the right along that straight line. So, again, kind of reviewing what we talked about earlier. So when a particle is, a moving charged particle is in a magnetic field, okay? And it's always remaining in the field. It's not falling out of the field. It's always in the field. What happens is, by the right-hand rule, right, if you do V cross B, right, B is into the page, V is to the right, you will always get a force pointing towards the center, a center-seeking force, okay? And that center-seeking force basically curves the path of this charged particle into a circle. And so what you have is you have uniform circular motion, and then you have a bunch of really cool applications that, unfortunately, we're going to skip for this part of the chapter just for the sake of time. Okay, but really this is kind of what you need to know here is that particles in a magnetic field, they will basically start moving in circular patterns. We're going to skip this example. Like I said, we're skipping a few sections in this chapter, okay? So don't worry about this example. What I want to get to is this example related to this. So let's move back to forces again, all right? We are generalizing the force on a moving charged particle, and we're generalizing it into a conductor that's carrying a current, which, as you know already, is a bunch of charges moving with a velocity, right? So this section of conductor is going to feel a force. Okay, and we can do some conversions to see that the force on a particular segment of wire is IL cross B. So it has the same form as QV cross B, right? Except all we did is we interchanged QV for IL. All right? Where I is the current and L is a vector that defines the length and direction of that wire segment. So, but you're basically doing the same cross product, except you're just using slightly different geometric variables. So let's do this example here. All right, so in this example, we have a copper rod. The current is 50 amps. The direction of the current is from left to right or west to east. And we're told that there is a magnetic field that's pointing 45 degrees to the length of that segment. And its magnitude is 1.2 Tesla. What is the magnitude and direction of the force on a 1 meter segment of rod? And then what would be how would we need to move this rod around in order to get the maximum force? So let me go ahead and switch to okay. So here's our problem. So basically, right, we're asked to find the force on a length of current segment of a rod. Okay, so we're going to be using IL cross B to determine the direction and magnitude of that force. And so let's write down what we know from the problem. Well, we know that I is 50. And And we know, okay, and that 50 moves from west to east, okay? So what we could do if you wanted is we could, instead of using northeast, southwest, is we could throw a Cartesian coordinate system on here. All right, and what we could say is that our L vector is the length of the rod in the x direction, right? I hat. What's the length of the rod? It's the 1 meter section, okay? So basically, our L vector is 1 meter I hat. We're told that the magnetic field is in the direction of the northeast, so 45 degrees north of east. So that makes our B field have an X and a Y component, right? So let's see if we can express our B vector just as some good practice. Let's express our B vector in terms of components of X and Y. So, so B is going to be the X component of B in the I hat, and then the Y component of B in the J hat. How do we figure out the components? Well, we build our triangle, right? The hypotenuse of B is the magnitude of B, which was 1.2 Tesla. Okay. This would be the X component. This would be the Y component. And it's a 45-degree angle. So we don't really need to use similar triangles here. I mean, right, because we have the angle. So we can just straight up use our sines and cosines to define our triangle, this particular one, right? We don't need a second triangle. We have all the information we need to find the sides of these triangles. So BX then would be the adjacent side of that angle, 45. So BX would be B cosine 45, and BY would be B sine 45, which I believe is square root of 2 over 2, right? So BX would be 1.2. Let me go ahead and put that in the calculator. I'll write it out first. 1.2 cosine 45 I hat plus 1.2 sine 45 J hat, which comes out to be 0.849 Tesla. What? I put meters here. I don't know why I did that. Obviously, it's Tesla. So, and then sine of 45 is the same as cosine of 45. So we get the same business for the J hat. All right, so now that we have everything written in vector form, we can go ahead and compute F. So F is IL cross B. So I is a scalar, I is 50 amps. And then we're doing L cross B. So L is, let's see, L is 1 meter I hat. And we're crossing that with B. And so algebraically, how we do this cross product is, oh, that's a plus, is we're going to distribute the cross product. Okay, so we're going to do I cross I plus I cross J. Okay, so let's write that out. Okay, I'll just leave them out to the side. So we're going to do 1 meter times 0.849 Tesla I cross I plus 1 meter 0.849 Tesla I cross J. Okay. Well, what's I cross I? It's 0, right? So this whole thing is gone. And all we're left with is 50 amps times 1 meter times 849 Tesla in the I cross J direction, which happens to be K hat. How do I know that? Here's the trick. Okay, if you're going clockwise, crossing, your result will be positive. So I cross J will give me K. Okay. So the force then is 50 times 0.849. 4245 Tesla in the K hat. Magnitude 4245, direction in the K hat. So what about part B? While keeping the rod horizontal, how should it be oriented to maximize the magnitude of the force? Keeping the rod horizontal. I guess what they mean is, by keeping the rod in the XY plane and rotating it either this way or this way, okay? To me, horizontal, when I first read this problem, I was thinking horizontal just means like this, but I think what they mean is in terms of northeast, southwest, horizontal would be rotating in the plane of the northeast, southwest and not popping out of the plane, okay? So the question is, how do we maximize the force, all right? Well, let's rewrite what the force is, right? The force is IL cross B. Magnitude of the force, right? Using the cross product definitions, ILB sine theta, where theta is the angle between L and B. So to make sine theta the biggest, right, we need theta to equal 90 degrees. So what we need is the angle between L and B to equal 90 degrees. And, right, because sine of 90 is 1. So let's look at our picture. To make the angle between B and L 90 degrees, we need L, so we're moving the rod, but we need L to be like right here. Right, so we need to rotate the rod 45 degrees to the south, right? That would make this angle here 90, and therefore we would maximize the force on that rod, okay? So we've been working with cross products, all right? We've been talking about forces on moving charges that are living in magnetic fields, and then we kind of went back and forth and talked a little bit about the fields themselves. So I'm gonna stop this video. Let's talk a little bit about this. This is fun. This is not stuff on a test. So you turn it off if you just care about your time in the test. If you are interested in how magnets work, I will give you a brief explanation. So you may recall in the very beginning of the first video lecture in chapter 27 is I said that moving charges create magnetic fields, right? So if that's true, how do magnets work, right? How does a refrigerator magnet work? there's no current, right? You don't touch that refrigerator magnet and feel a charge. You don't feel current, right? You're not getting zapped when you touch a bar magnet. So there's no current there. Where's this field coming from? Something is moving, right? There's some charges moving. Where are they from? Well, the charges that are moving in magnetized objects like iron is the electrons orbiting the atoms of the iron, okay? And so when you have an unmagnetized piece of iron, you have a bunch of little magnetic fields that are created by, let's see, this is the iron nucleus, okay? And then you have a bunch of electrons orbiting. I'm only drawing one, right? You have a bunch of electrons orbiting the iron atom. Well, a couple of them orbit in a special orientation, okay, which is typically an f orbital or a d orbital. And what that does is it creates a current, right? Because you have a moving electron moving in a certain region. It creates a current, and then the right-hand rule to that current creates a magnetic field, right? And so the magnetic field is coming from the certain electrons orbiting the nucleus of the iron atom and other magnetic atoms, okay? But I'm just using iron as an example. And in an unmagnetized piece of iron, so maybe a piece of iron that you find laying around in a metal yard, or, maybe a piece of stainless steel or something, right? Not magnetic off the bat. And that's because each of the atoms in that piece of metal, they're kind of like oriented in a slightly different direction. They are just randomly oriented in that piece of metal. So those little magnetic fields add up to 0. Okay? So that's what you see, the little arrows, the little magnetic fields, they'll add up to 0. There's no net direction. But there's several different ways you can magnetize a piece of iron, right? You can heat it up and get those atoms loose and put it in a magnetic field, and that would force all the electrons to start orbiting in the same pattern, producing a magnetic field in the same direction. And then you have this net magnetic moment where you have that super attractive force either on the positive side or the negative side, right? Where you can bring a paper clip and see that force of attraction. So basically, magnets. How magnets work is that certain atoms like iron, cobalt, nickel, there's some other ones like neodymium, okay? They have a special orientation of their outermost orbitals. And if they're all happen to be pointing in the same way, they're going to generate a current in that same direction and add up all the magnetic fields they create and get a net magnetic moment. Okay, so that's really how magnetic fields are created, by moving charges, okay? They're either created by the moving charges in the valence shells of electrons, or they're created by us applying a potential difference using a battery or a power supply, applying it to a conductor and getting electrons to move that way. Okay, either way, magnetic fields are created. All right, so if you have any other questions about that, let me know. I'd be happy to point you to some resources if you're interested in magnetism. I have a bunch of good videos to share with you, okay? But for the test, you don't have to worry about that. All right, so I'm going to move on to chapter 28.